Hello everyone, welcome back. Let's talk about another easy problem on Leetcode today. Subtree of another tree, Leetcode 572. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given roots of two binary trees, root and subroot, and we should return true if there is a subtree of root with the same structure and node values of subroot, and false otherwise. A subtree of binary tree is a tree that consists of a node in tree and all of these nodes descendants. A tree could also be considered as subtree of itself. Let's visualize this with an example. Here for the given root and subroot, we can find the subtree in the tree starting from this node. If you look at the node with value 4 in the main tree, the subtree starting from here is identical to the subroot because the structure is same and the node values are also same. We have node 4 here with two children 1 and 2. But in case the node values were different, for example, if instead of 2 here we had 3, then we wouldn't have found the subtree and returned false. Or if the structure was different, for example, we had 0 as a child of 2. So even though this tree and this tree are partially same, the structure is not same because this 2 in subroot doesn't have any children, but this one has one left child. So in these kind of cases where we don't have an exact match, our answer will be false. Now, in terms of solution, a straightforward way to solve this problem will be to go through each node in the main root tree, and at each node we ask the same question. Is the subtree starting from this node identical to our subroot tree? And to find this answer, we can use a helper function. Let's call it isSameTree. This function's only job is to take two tree nodes and determine if the trees starting from them are exactly the same, both in terms of structure as well as values. I've already covered this exact helper function in detail in the SameTree video. If you are interested, please check out the I button or the video description to watch that video. So here, for example, we start with the root node 3 and now we check if the tree starting from this node is identical to the subroot tree using this utility function. And this function first compares the node 3 with node 4, which are not identical. So it will return false. And since that wasn't a match, we move to its children to perform the comparison, say with the left child first, and again ask the question, is subtree starting at node 4 identical to subroot? So the SameTree function compares the root values 4 versus 4 and they match. So now it must check the children. So it recursively checks the left children in both the trees and they also match. And now this node doesn't have any children. So it backtracks and compares the right children which also match. And since the root values and the descendants are identical, the SameTree function will return true. And because we get a match, we will return the answer from the main function as well. Now the time complexity of this approach is O of m into n, where m is number of nodes in the main tree and n is number of nodes in the subroot tree. Because for each node in the root tree, we have to call the SameTree function, which in the worst case will take O of n time to check if the two trees are same, and we are doing it for m nodes in the main tree. So because of this, the time complexity is O of m into n, and the space complexity will be O of m, mainly coming from the depth of the recursion, which can go as deep as height of the main tree. And in the worst case, when the tree is skewed or unbalanced, the traversal on the main tree can go m levels deep. And at each level, we call the SameTree helper function, which can go n levels deep, resulting in the space complexity of O of m plus n. However, in the worst case, the depth of the subroot tree will be same as that of main tree, resulting in the space complexity of O of m plus m equal to O of m. Here is a quick code walkthrough of the algorithm we just talked about. with Java code on the left and Python on right. First, we handle the base case, which is if the current root node is null, that means we have reached the end of the branch without finding the subtree, so we will return false. Next, we call the helper function is same tree to check if the tree at the current node is identical to our subroot. If it is, we have found our match and we return true as the answer. Otherwise, if it is not a match, we need to keep looking. So, we recursively call is subtree function on the left child and the right child. And note that the OR condition is the key here. If we find the subtree in either the left branch or the right branch, the whole expression must become true. And we have successfully found our answer. Now let's also look at the is same tree helper function, which compares two tree root nodes P and Q. The first base case checks if both nodes are null. If they are, it means we have reached the end of both branches at the same time. So they are identical along this path. Hence, we will return true. The second base case handles all mismatches, which are if one node is null but the other isn't, or if there are values which are not equal, then the trees are not same and hence we will return false. And finally, if the current node themselves match, then we must confirm their children do too. So we branch out and recursively call this helper function on both the left children and the right children. And here note that we are using the AND condition because both left and right subtrees must be identical for the entire tree to be considered the same. Now the recursive DFS approach we just covered is a perfectly valid solution. For an easy rated Leetcode problem, it is clear, intuitive, and often all you need to pass the test cases. However, what if an interviewer asks to optimize it, telling that the root tree might have billions of nodes? Then the time complexity of O of m into n could become a real bottleneck. So let's explore a more efficient way to handle those scenarios. And the bottleneck in the first approach was repeatedly comparing nodes, which we can avoid by changing our perspective. Instead of comparing trees node by node, what if we could represent the structure and values of each tree in a more compact form, like a string? And this idea is called tree serialization, where our plan is simple that we convert both the trees, root and subroot, into unique strings, say by performing pre-order or post-order traversal. Both of these traversals work because they keep the root's value at a fixed position relative to its children, which results in an ambiguous string. However, we cannot use in-order traversal here because the root's value is placed between its children and it can produce the same string for different tree structures, making it ambiguous. And once we have these strings, the problem now becomes much simpler, which is to check if the subroot string is a substring of root string. And how do we perform pre-order traversal? It is simply by going from parent, then to the left subtree, and finally to the right subtree. So we go from 3, then we go to 4, 1, 2, and then 5. So this gives us the pre-order traversal. Similarly, the traversal of the subroot tree gives us 4, 1, and 2. And now we can see that 4, 1, 2 is present in the main tree's pre-order traversal. And now when we combine these nodes into a string, we may run into problems. For example, how do we distinguish the node values 3 and 4 from 34? So to solve this, we need a separator where we can use special character like hash, and then we can get the node values as hash 3, hash 4, hash 1, and so on. So this takes care of the values. And crucially, we must also represent the null nodes using some other special marker like the character n. So if we encounter a null child, we'll append a special marker n to the string, and this is vital to preserve the exact tree structure. So now that we have taken care of the values and the structure, we can serialize the root tree to following and subroot tree to following. And then we can see that serialized value of subroot is substring of serialized value of root. Hence, subroot is actually a subtree of root tree. Now the time complexity of this approach is O of m plus n, because serialization of both trees takes O of m and O of n time respectively. And then the substring search will take O of m plus n time if we use Knuth-Morris spread or KMP algorithm. And the space complexity will be O of m plus n as well, because we are storing the string representation of these two trees. And now I haven't covered the tree serialization or advanced string searching algorithms like KMP in detail yet, but we'll definitely get to them in the future. For now, the key takeaway is that we are transforming the tree problem into a string problem. And for now, we can simply rely on built-in contains or find methods that most programming languages provide, as they are highly optimized. Now let's walk through the code for serialization based solution. First, we'll initialize two string builders or list of strings, one for the root tree and another for the subroot tree. Next, let's call the serialize helper function on both trees to populate these string representations. And finally, we convert these string representations to actual strings and check if subroot string is substring of the root string. In Java, this is done easily with the contains method, and in Python, we can use the simple in operator, and the result of this check is our final answer. Let's also quickly look at the serialize function. This is basically the standard pre-order traversal, where we check if the current node is null, we append the special marker #n to the string, and this is crucial for capturing tree structure accurately. Then, if the node is not null, we append a separator hash followed by the node's value, and then recursively call the serialize helper function on the left child and the right child, and this node left right order is what defines the typical pre-order traversal. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.